recording. Right. So the last chapter for us is about talking a little bit about this, the beginning of the universe, which we called as the Big Bang theory. And at the same time, we will talk about the expansion of the universe and different models about the universe and what will happen to universe at the end, right? So the reason is like you can't get one of these topics separately because they are kind of connected to each other, right? To start with, so this image right here is probably maybe new to you, and this is called James Webb Telescope, right? And the reason that I have put this one here is this is the huge web-based telescope, which is actually scheduled to be launched probably in this next month or within this year. You will hear this news in the, news in the media probably, I guess maybe very soon. Uh, and this is actually a successor to Hubble Space Telescope. All of you know the Hubble Space Telescope, right? And this one is actually going to replace the Hubble Space Telescope, but this is, you know, that the primary mirror of the Hubble Space Telescope is around like 2.4 meters, but this one right here will have a 6.5 meter mirror, right? The reason that I put it here at the beginning is that this is going to observe the universe in very high redshift, which means the things that you have at very close to the beginning of the universe. So this particular telescope will be capable of observing those, right? So which will be probably change or maybe confirm some of your ideas that you are going to uh, learn in this particular chapter or the section. Right. Now, so let's talk a little bit about cosmology. Now, in previous chapters, we have explored that the different contents of the universe, right? So we started from talking about planets and then move into talk about like different properties of the stars. And at the end, actually, we talked about galaxies and then galaxy clusters, right? And we also learned that how these objects change with time, right? For example, remember that we kind of learned the whole process of stellar evolution, and then also we learned about what happened to galaxies over the time. So they merge together and they collide together, and then they gravitationally bound into these clusters of galaxies, those kind of things. Now, uh, so what we are going to talk or discuss today is how about the universe as a whole. So if you take the universe as a whole, so we are going to talk it as a whole, one unit today, right? And the questions that we have to answer is basically how old is the universe and what did it look like in the beginning, right? So how was it look like in the beginning? So where did it begin, and how has it changed over the time, right? And what will be its fate, right? So what will happen to our universe in future, right? Those are the basic questions that actually have we should have when we like learn about cosmology. And the cosmology is all about like answering these questions if you kind of get the basic idea of that, right? And so we will describe what we already know about the history of our dynamic universe, and also we'll highlight some of the mysteries that still remain, right? Such as the dark energy and those stuff. Right. Now remember that we talked about this expansion of the universe in last section as well when we talk about the Hubble's law. Now, before these observations done from Hubble in 1920s, actually astronomers did not know that the universe was expanding at that time, right? So because it is Hubble actually who observed these galaxies from his telescope and then figured out that our universe is expanding. And before that, we did not know about that, right? Now, when we talk about the general theory of relativity introduced by Albert Einstein, so this has happened around 1915. So which means some years before Hubble found that the universe is expanding, right? Now, because of that, actually Einstein actually has changed his equations in this general relativity by introducing a new constant, because he had this kind of insight that we are living in a static universe, right? So it should not be expanding. So that was his idea. So because of that, to kind of so he was kind of inclined to add this extra constant, so which we now call as the cosmological constant, just to represent the static universe, right? Now this constant, actually, if you look at that particular constant, what it represents is a force of repulsion to balance the gravitational attraction on the largest scale, right? We know that the gravity always attracts things. So from this constant, he tried to have a kind of introduce a hypothetical force uh, which is a repulsive force to balance the gravity, so that you will be in a static universe, right? So that's the idea. Now what will happen is this would permit all these galaxies to remain at a fixed distance from one another. So that was his idea, Einstein's idea at that time. However, when Hubble reported that the universe is expanding, uh, so once when the universe is expanding, you don't need that, right? Because when it is expanding, you don't need to balance these two forces. And because of that, actually, Einstein later reported that this is probably the biggest blunder of his life, about adding this extra constant, right? Which was not there, because according to Hubble, his original equations should have been correct. So that's the idea. And now, if we keep that in your mind, if we let's say you make a movie that about the expanding universe, and then if you ran it backward, so we can think about what we can see, right? So you probably see that uh, maybe galaxies, instead moving apart, maybe would move together in our movie, right? Because you know that when you running it backward, all these expansion will go towards the backward direction, right? So this is just something that you have to imagine, not what actually is happening. So everything is expanding, but if you go to the backward direction, all the things should be contracting, right? And so eventually what would happen is all these things uh, will be contracted to a very small volume. So we used to tell that eventually we would find that all the matter we can see today will concentrated into an infinitesimally small volume, right? So just think about if we are in expansion universe, however, if we make a film that runs into the backward direction, so we take everything towards a very small or infinitesimally small volume when we go towards the beginning of the universe, right? Now this is what astronomers think as the beginning of the universe, right? So if you go backward, so everything will be concentrated into a very tiny volume, and astronomers think that that should be the beginning of the universe, right? And uh, so so what we now predict is that the explosion, when we have this concentrated small volume, then there is an explosion in that, right? And this explosion that concentrated universe at the beginning of the time is called as the Big Bang. So there was everything was under a very tiny volume or infinitesimal volume, and then there is an explosion at that particular time, which is what we called as the Big Bang, right? Now, this is what I mean. If you need to get a basic idea, this is what we called as the Big Bang. Now, the next question is, when did this occur, right? When did this has happened, at what time? So, right, so that is the next question, right? Now to answer that question, we have to look at the age of the universe, right? Because if once you go backward and backward, you should find like we should have a certain time period for our universe since the Big Bang, right? Now if we need to get a rough estimate, now we know that at that particular time there were no humans around to look at their watches and start like counting the time, right? So because of that, we are going to use the Hubble's law to find the age of the universe. Now this is a way of estimating the age of the universe very roughly. That is, let's assume that the age of the universe as t naught. So you have an age as the t naught, and then you have to assume that the expansion rate is constant. So we assume that according to the Hubble law, the expansion rate will be constant. I mean, you know that it is not true, right? Because we already learned that depend in different times you will get Hubble constant will be different slightly, but for the time being, let's assume that the Hubble this expansion rate is constant, right? Then let's assume that the time it has taken a galaxy to move, so I have mentioned it here, the time it has taken a galaxy to move a distance d away from the Milky Way is equal to d over v, right? So this is the simple equation that you know, right? If an object moves a distance of d at a speed of v, the time it will take to move this distance, if that is t naught, that will be equal to d over v, right? Now v is the velocity of the galaxy. Now if you look at the Hubble law kind of relates v and d with the Hubble constant right here, which you already have learned in the last lecture, right? Now combining these two expressions, which means this expression and this one right here, you can plug the value of v as h times d, which will come as t naught equal d over v, which is equal to 1 over h, right? Now basically, just by taking the reciprocal of the Hubble constant, you can estimate the time of the universe. The only thing is you need to be careful with the proper units that you are going to use, right? So that is it. And now you know that this is not the most accurate way of predicting Hubble law, right? And the age that we estimate in this way is what we call as the Hubble time, right? So you can get a rough estimate, right? Now, what we know here is Hubble constant is now roughly closer to 21 or 22 kilometers per second per million light years. Now, if you plug that value right here, you will get an answer. I mean, this is not a hard calculation, right? You can just go and plug in the numbers and you can get the answer. And if you check the calculation, you will get a value something very closer to 14 billion light years, right? So 14, not light years, 14 billion years. So that is the rough estimate for our age of the universe, right? Now, as I told you, this Hubble time is the right age for the universe under one condition, that is only if the expansion rate has been constant throughout the time since the expansion of the universe began, right? Now if we assume that just after the Big Bang universe has started expanding, and if this expansion rate is constant throughout the time period until now, then this Hubble time or the age of the universe that we estimate using this method will be correct, right? And but you know what has happened is actually when we think about this, astronomers actually expected that the rate of expansion should be slowing down, right? Now this is because you know all these galaxies, when they are very close by, they are mutually attracted because the gravity is a kind of acting as a repulsive force against to this expansion, right? Because of that they expected that this expansion should be slowing down, right, after some time. Now the reason is this mutual attraction between galaxies. Now I guess all of you can understand it, right? The gravity is always an attractive force, and it is the expansion is going against that, and because of that astronomers thought that this expansion rate should slow down due to this reason. Now what that means is if we use this current rate of expansion to estimate the how long it took the galaxies to reach their current separations, we are actually overestimate the age of the universe, right? If this is true, which means I mean, what we expect is due to the gravity, this expansion rate should have been slowed down. So which means our age should be not much as we estimate uh, from this Hubble law, right? So that is the idea that we astronomers had. And so here are the two pioneer kind of people who actually worked on this one. As you know, Einstein from his general theory of relativity with all this theoretical work, and then using the expansion of the universe, I mean finding the expansion of the universe by Edwin Hubble. Right. Now, remember now this is like a story. First you have estimated the age of the universe as 14 billion light years, depending on the Hubble constant we have, assuming that the expansion rate is constant. But at the same time, astronomers had an idea that this expansion rate should have slowed down, and because of that, we should be overestimating the age of the universe, right? I guess you can understand it. Now they wanted to check this, right, whether this is correct or not. So what they have done is actually, and to check this they need some more data, right? So that is the idea. So that is so they have what they have done is basically they expected they need to know, they need to have two things. The first one is they should have larger telescopes so that they could measure the redshifts of more distant galaxies, right? Now this is why this James Webb telescope will be important in future. uh, you know that the redshift is normally measured using the spectroscopy, which means you take a spectrum of a galaxy and then you look at how much the redshift is, right? So that is the idea. Now get a spectrum of these very galaxies that are so far away. You need to have a very large telescope to look at far and far away, right? I guess you probably remember that we learn about these things under instrumentation. And the other thing is, so you can measure the redshift, and the other thing uh, they thought is that you should have a very luminous standard light bulb. Now what this means is actually we also used to tell these as standard candles. These are actually some kind of astronomical objects with non-luminosity. Now, the perfect example for this one is the type 1a supernova. If you remember that we talked about type 1a supernova under the star formation process. This type 1a supernovas normally uh, occurs by having a white dwarf with the close companion of another star. When it has enough matter that can accrete towards this white dwarf, the complete white dwarf will explode, and which will give you this type 1a supernovas, right? And remember that this type 1a supernova has a certain light curve, and I have mentioned there this story that astronomers used to use this type 1a supernova as distance indicator, because their luminosity is kind of constant. We know that value, right? Because of that, if you find a distant supernova in a galaxy, you can compare the apparent brightness with the known brightness to find the distance to that particular galaxy, right? Now that is an example for these standard candles. So these are like standards that we use to measure distances, right? Now if you have these two things, you can actually measure these distances to these galaxies that are far away, which we can get an idea, right, whether our current estimates or current predictions are correct or not, right? Now the idea is that if we compare how luminous a standard light bulb, think about that as the distance measured uh, from these supernova explosions type 1a, standard bulbs is supposed to be an, and how dim it actually looks in our telescope, the difference allows us to calculate the distance, right? Once again, this is directly related to these distance calculations we discuss in star formation process, right? So if you get the apparent brightness, and if you know the actual brightness, now this for type 1a supernova, we know the actual brightness, and if you get the apparent brightness, then from the difference you can calculate the distance. That is the idea, right? Now, so they had to wait until 1990s, right, to satisfy these two requirements, right? To look at have to make distance measurements using type 1a supernova, and also take spectrums to measure the redshift of these galaxies that are so far away from us, right? So astronomers showed that the type 1a supernova, with some corrections based on the shapes of their light curve, are standard light bulbs. So that is, we already learned in one of the previous chapters, right? And then if you have this large 8 to 10 meter telescopes that can be used to obtain the spectra, we can measure the redshift of those galaxies. So you have to have a supernova in one galaxy, and also you should be able to measure the redshift of that particular galaxy as well, right? So these two will give you two independent measurements for the distances. That's the idea, right? And because you know that when you know the redshift, you can calculate the distance as well, right? But that's depend on the expansion of the universe. And so what researchers actually found for them, they were actually surprised with the result, because they found that when they look at this type 1a supernovae in distant galaxies, they were actually fainter than they expected from the Hubble law, so which is the measurements getting from the redshift, right? So what this means is, if this is fainter, you can understand, right? I mean, if something is fainter than you expected, which means they should be more far away than you have expected. So which means the universe has expanded more than you expected, because that's why they are more fainter, right? When you look at those. And instead of actually the slowing down, the final conclusion was the universe is actually accelerating, not slowing down, right? So that is the interesting result here. And I guess you can understand this story logically, right? So what they have seen is this faint, the supernova was actually faint than they expected. So that means they are so far away from us than you expected from this Hubble redshift relation, which means these galaxies are actually, uh, I mean, have gone far away than you have expected from this, even from the constant expansion rate. So which indicates us, uh, instead of slowing down the expansion rate, the universe is actually accelerating, right? And this is actually not something unexpected for astronomers. And they actually first resisted to considering it, and they were looking at some of the other possibilities at that time. Maybe they have uh, measurement errors and those kind of things, but actually what's happening is, according to their results, the universe is now accelerating. Now here is a image that shows you clearly uh, each galaxy and its supernova, right? So there are a few galaxies that they, I mean, as an example, that you have a galaxy and you have a supernova there, and then the bottom row you can see the same galaxy, so you can compare the same galaxy either before or after the supernova exploded, right? So they use this supernova to take these distances. These are just like example images. Now there is a problem again, right? So we were expecting that due to these gravitational forces, not universe will not have a constant expansion rate. Instead it will slow down. So that is what we expected because of the gravity, right? Or the attraction between galaxies. But what they have actually found was universe is accelerating, right? Now, you know that if you want to accelerate, let's say you need to accelerate a car, so you have to supply some extra energy, right? So that's what we do by pressing the accelerator or giving some extra more gas into that to accelerate the car, right? Now similarly, if you think about this acceleration of the universe, there should be some extra energy that we have to supply for this acceleration, right? Which is unexpected. Now, because of this acceleration, scientists call whatever the energy that is responsible for this acceleration as the dark energy, right? Which is, I mean, you can see from the name itself, the name dark energy came out because we don't know anything about it, right? So only thing that we knew at that time was this: there should be some kind of energy that will be responsible for this acceleration of the universe. So that is the idea, right? Now this new component of the universe, you have to remember that this is not the dark matter, right? So don't get confused with these two. So the dark matter is something else that we talked earlier, right? Because sometimes students get confused with those two words because they have two different purposes. Dark matter is what you had inside these galaxies that that are invisible matter, but at the same time they are responsible for this extra gravity that creates, right? That's what you have seen from these rotation curves that we discuss under galaxies. Now here, the dark energy is a different thing, right? So the dark energy is something else that we have also not yet detected in our laboratories on Earth. And at the same time, dark energy is responsible for expansion of acceleration of the universe, right? So there are two different things. Make sure that you understand it. And although these compelling evidence, there are compelling evidence that dark energy exists, we don't yet know the source of that energy, right? Only thing is that we know that there is dark energy, right? And the next thing is this acceleration now seems not to have started with the Big Bang, right? So it is something that probably have came later. So that's what we know up to now. And during the first several billion years after the Big Bang, when these galaxies were close together, gravity was actually strong enough to slow the expansion. You know that when two objects are very close together, gravity is more powerful, right? So we have the idea that this gravity probably uh, slow down this expansion initially, just after the Big Bang, right? And because the gravity is strong at that time when these objects or the galaxies are very close together. Now, when galaxies moved further apart, this effect of gravity should be weakened, right? So these things you should be able to understand from this basic physics, right? The gravitational force is proportional to inversely proportional to 1 to r squared, right? So we normally tell that it is proportional to 1 over r squared, which means when the distance increases, the effect of the gravity should be weaker. So that is what has happened here, right? Now, so what has happened was, so this gravity was initially very powerful and then it has gotten weakened. And after several billion years, after this Big Bang, then dark energy has took over, because when the gravity got weaker, the dark energy took over and the expansion began to accelerate. So this is the idea that we have right now about our universe, right? Now, what we know right now is the current estimate is that the universe is around 13.8 billion years old with an uncertainty of about 100 million years, right? And just to keep in mind, there are some numbers and some information that I mentioned here is, I mean, I'm not going to go into too much details, but just to logically remember these things, I kind of tell you some of these things in more detail. So just right now, this is the idea that we have. If you look at this diagram right here, this is the place that we believe where the Big Bang has started. And after that, there is a small period, which is a very tiny period that we think that there is a region that we call as inflationary universe. Yeah, the inflationary universe means actually the universe has expanded an enormous amount within a very short period of time, right? And that's a different story, which is not, I have not talked here. And after that, you can see that this curve is kind of, you know, the expansion is slowed down until this point right here, and then it started somewhere here. I mean, around this is present universe that what we have, and then it has started to accelerate. like that, right? That's why this curve has gone up in that way, right? So this is kind of a the rough idea that you should have about our universe after the Big Bang, right? And this is the time axis. That's why it says 13.8 billion years up to around now, and then we believe that it will be accelerating, right? Now, so what we know up to now is, in summary, we have this dark energy, and we think that the universe has universe is expanding, but the rate of expansion is not actually slowing down or constant. Instead, now it is accelerating, right? Initially, it was actually a little bit slowing down due to the gravitational force, but when the gravity got weaker, it has started accelerating, and now we know that our universe is around 13.8 billion years in terms of the age. And now another way of like looking at the age of our universe is the knowledge that we have about these star clusters, right? Remember that in our galaxy and other galaxies, the oldest star that we found is in the globular star clusters. Remember that in the topic about the star clusters, we talked there are basically two types of star clusters. The first type is open star clusters, which are relatively consist of relatively new stars and hot young stars. But for the globular clusters on the other side, they actually have older stars, and they are probably the oldest stars that you can found, right? Now, in this recent uh, developments in astronomy, now as astronomers can use different methods to age the estimate of these globular clusters, right? And so the conclusion is that these oldest stars that are formed in these globular clusters are around 12 to 13 billion years ago, right? Now, this kind of agreed with the current age of the universe that we have, because we can think that these older stars in globular clusters, so they probably did not form until the expansion of the universe had been underway, right? At least for a few 100 million years, because stars are not the first thing that has formed. So initially there were few steps that you need to go for this formation, and it took some time for these first stars appear in the universe. So which means the age of these globular clusters or stars inside this globular cluster should be little less than the age of the universe, right? And because of that, the age of the universe, we know that the 13.8 light billion years, and this is kind of consistent with the age of the globular clusters that we know, because the age of the globular clusters are a little bit less than what we little bit less than the age of the universe, right? Right, so this is just an example of a globular cluster, and you can see that this spherical shape of the cluster and everything here, right? I mean, these things we discussed earlier, right? Now we have, I expect that you have some kind of knowledge now about this idea about the expansion of the universe, right? Now let's look at this, use these results and then apply those to develop a model for the evolution of the universe as a whole, right? So this is just we are trying to get a model of the universe to look at, I mean, what happens to the universe from the start and also towards the future, right? So when you think about a model for our universe, we normally expect that there are few things that it should be, I mean, it should satisfy. The first thing is this particular model should include the expansion that we observe, right? I mean, that's obvious, no? We know that the universe is expanding, right? So that is something that we already know. So our model should include that. And the second thing is the cosmological principle also should be valid. Remember the cosmological principle that we talked last lecture, that is universe is homogeneous and isotropic, right? So that is the cosmological principle. And because of this cosmological principle tells that universe is everywhere looks like the same, we can just take a sufficiently large portion of the universe and then go with that for any explanation, right? Because it will be same in everywhere. And now to describe how the space stretches, we say the cosmic expansion causes the universe to undergo a uniform change in scale over time, right? Now, if it is not clear, this thing about the scaling the universe, just think about an example like let's say distance between two galaxy clusters is r, right? So you have one galaxy cluster and you have another galaxy cluster, and assume that the distance between these two galaxy clusters is equal to r. And so if r doubles, r is the scale now, right? If r doubles, then the distance between the clusters has doubled. So that is the idea, right? If r doubles, the distance will be doubled. And since the universe is expanding at the same rate everywhere, the change in r tells us how much it has expanded or contracted at any given time, right? So that is the idea. So you get two clusters and the distance between r, and if the universe is expanding in the same rate, then the change in this r tell you how much it has expanded, right? So that is the idea, right? Now this expansion will also affect to redshift. Now something that I need to mention briefly here is that uh, what actually happens when this universe expands is that these waves also get stretched due to expansion, right? So it is not that once they travel, they get, I mean, this expansion basically happens because of the stretch of the surface. As you see in these two diagrams, now this one is the expanded one. So it's the same wave, but now it is more get stretched. And that's why the wavelength wavelength looks more redder because it gets straight. Now, that's why I have mentioned here the more accurate view of the redshift of galaxies is that the light waves are stretched by the stretching of the space they travel through. Right? That is the reason why you have these large redshifts because of the expansion. I mean, redshift basically gives you an idea about the expansion of the universe, right? So that's what I want to tell. Right. Now, depending on the information that we have, so there are four possible models that we can think of. And these are the four possible models. First one is right here, second, third, fourth. And this yellow star type of thing is where you have this Big Bang or the explosion, and this yellow square is where we are present, right? It's kind of for all four models. And we have measured the time in this vertical direction, and the past is here and the future is in this direction, right? And the one in this left hand model tells us that the universe will start to expand, and then there will be some point it will stop the expansion and then go into the other direction, right? So which means it will contract and will come to the same position again, and we call this as the big crunch, right? I mean, you can see the details here as well. And the next one is slightly different than the first one. So that is the universe that may be expanding forever, right? It will slow down. You can see this curve is kind of bent towards this direction. So because of that, it will actually eventually slow down, uh, but it will not come back as the previous one, right? So which means it will continue to expand forever, right? So that is what happens. And then you will have this third one. So that we usually tell this as the coasting universe because the expansion rate is constant and it will continue to expand like this, right? I mean, this is what was our assumption when we were using this Hubble time. right? The expansion rate is constant kind of thing. And the third one is due to this dark energy, the Big Bang has started here, but it will start to accelerate at the end, right? And so that's because that's what we have as the last model. So there are four possibilities, as you can see, and so I have explained it here in these two slides. So astronomers look at the average. There is a way actually that we can explain this thing. Astronomers or cosmologists normally look at the average density of the universe to determine the kind of universe that we live in, right? Now, this one is actually the proofs are kind of related to the general theory of relativity. So I'm not going to take those equations into here, but I will explain you what happens here, right? And so astronomers normally look at the average density of the universe to determine the kind of universe that we live in. And this is actually the mass of the matter that would contain in each unit volume if all the stars, galaxies, and other objects were taken apart atom by atom, and if all those particles along with the light and other energy were distributed throughout all of the space with absolute uniformity. I mean, the idea is you take the mass per unit volume, right? So that is the density, right? And we assume that everything is like in the space will be distributed uniformly, and because of that you can take the density by using a tiny volume, right? Now, so what we get as a result here is that if this average density is low, right, there is less mass. You know, that's the idea. Now, if the density is low, there is less mass and less gravity, right? I guess you can understand it. If the density is low, there will be less mass and less gravity, and the universe will not uh, deaccelerate very much, right? It can therefore expand forever. That is the first idea that we can get based on this density. And if you have a higher average density on the other hand, this means that there is more mass and more gravity. And because of that, the stretching of the space might slow down, right? Because you have enough gravity to slow down that, right? And we can tell that the expansion may eventually stop due to this reason. And if you have very extremely high densities, then what can happen is the universe may collapse again as well. Now, if you look at these diagrams, these two are the things which when you have very high density, then gravity will take again. So two things can happen. If either it will slowly expand forever, or it will expand and then contract again, right? Due to this gravitational effect. Right. So just to reiterate what I have tell you, if it is not clear, if the density is low, then you have less gravity. Because of that, the universe will expand forever. And if the average density is high enough, there will be a time that you will have the expansion, but it will stop at some point. But if you have extremely high density, it will not only stop, it will contract again or collapse again, right? So that is the idea. Now there are different universes that we name based on this critical density. So there is something, there is a very specific density that we called as the critical density of the universe. Now for a given rate of expansion, there is a critical density. This critical density is the density that is just enough to slow down the expansion to zero at some time, infinitely far in the future, right? That is what we define as the critical density of a universe, right? Now, if the actual density is higher than this critical density, assuming that you don't have dark energy, then the expansion will ultimately reverse and the universe will begin to contract, right? And now this is, so what I am doing is further explaining these models. So once again, the critical density is the density that is just enough to slow down the expansion at some time infinitely far in the future, right? If the density of the universe is higher than this critical density, then the expansion will ultimately reverse and the universe will begin to contract. Now this is what you see here in this first model right here, and you can see the same thing in this graph. So there is the time in the right hand in the x-axis, and here is the scale of the universe, r, that we call, right? Now this first graph right here from the number 1 is that goes up expanding and then comes down again to the same position in terms of this scale, right? Y-axis will be 0. This is what happens if the density of the universe is higher than this critical density, right? So I will upload these slides. You can see that I have mentioned the curves and the figure numbers here for you to understand. And if the density of the universe is less than the critical density, so if it is density is less than the critical density, what will happen is gravity is not enough to stop the expansion, and this kind of universe is called as infinite, and also this model is called as open universe. Now the previous one is actually called as a closed universe, right? Because it will expand and then contract one day. But when you have a density that is less than the critical density, that is actually this open universe, which is actually curve 2 in the figure 8, and the second from the left in figure 7. Figure 7 is this one right here. So we are talking about this particular possibility, the second one, right? It will continue to expand, and yes, and especially you can look at it from here. The curve 2 is right here, the second one, this one right here. Right, and then if you have exactly the critical density, then what will happen is the universe can just barely expand forever. So that is curve 3 and figure 8, and this curve 3 is, what is that? So it will barely expand forever if you have the exactly the critical amount of the critical density, right? And now when we introduce this dark energy, the rate of expansion will increase with the time, and the expansion will continue at an even faster rate. So that is this fourth curve right here. You can see that it will slow down and then take on again, right? The expansion will be at a faster rate, right? So the rate scale dr over dt, if you take, that will keep increasing. That is the idea, right? Right, so this is just to get a rough idea what happens at different situations of the universe. And the critical density is normally defined from this equation. Now I have already defined this, but in terms of a mathematical equation, you can tell it in this way: observed density in the universe divided by the critical density. Sorry, the critical density is this one right here, but we can define this parameter omega as the ratio of the observed density and the critical density, right? And this way it is easy to mention what happens to the universe depending on this parameter, right? Remember that previously we told that when what happens when density is greater than critical density, density is smaller than critical density, and density is equal to the critical density, right? And let me explain this now using this omega parameter. And also you can find the critical density using this particular equation right here. And I'm not going to prove these equations. I'm just giving you some of these equations. And this is the critical equation for the critical density. And H is the Hubble constant and G is the gravitational constant, right? Those are the two things that you have to know for this, that equation to find the critical density. And indeed, if you have data, you can actually calculate this. Right. Now, let's look at the same things that we discussed based on this omega parameter. So if omega is, we call this omega as, by the way, cosmological density parameter, right? And if omega greater than 1, we used to tell that the universe has a positive curvature and is finite. And if omega equal to 1, the universe is spatially flat and infinite. And omega is less than 1, then the universe is negatively curved and is infinite, right? This is how normally, I mean, you sometimes you may not understand this complete story, because this is something that kind of combined with the general relativity as well. And the idea is, we will come back to this particular point again later in the lecture, right? So for now, just let me go and see. Right, so this is just an example like how we actually measure the redshift of different objects. Now Hubble's, this is an image from, I guess, from the Hubble Space Telescope. This is called Hubble Ultra Deep Field, that shows a lot of faint galaxies, and the small squares that you probably see in this image has mentioned it, their redshift values, and you can see that there is a one galaxy right here with the record redshift, right, 11.9, and this is probably the maximum redshift that we have observed up to now. And this particular, if this redshift is actually true, this is actually true because this is confirmed by some additional measurements as well. The galaxy that is seen with relevant to this particular redshift is around, this is just after 380 million years after the Big Bang, right? So which means when the universe is less than 3% of its present age, right? So that was one of the old, one of the most distant galaxies that we have measured using this Hubble ultra deep fields. Right, so that's kind of an idea that I gave you about this expansion of the universe. And let's look at the best evidence. Now let's look a little bit about what has happened during these early ages, right? Now we have enough evidence that the universe is expanding, and we have models. We can have some models to explain this expansion of the universe, right? Now, according to the evidence now we have today, all these things indicates that the first galaxies did not begin from until a few hundred million years after the Big Bang, right? Now that's why I have shown you this picture right here. The furthest away galaxy that we have detected is around close to the redshift equal to 12, which is after 380 million years from the beginning of the Big Bang, right? After the Big Bang, it has gone about 380 million years for this galaxy to appear, right? So what we know is from that is these first galaxies did not begin until few hundred million years after the Big Bang, right? So that what we know. Now, what were things like before there were galaxies and space had not yet stretched very significantly? So what we are going to talk now is what we had before that, before the galaxies, right? So we know everything that up to the galaxies, but what we don't know is what was there before the galaxies, right? Now, scientists now have actually been able to calculate some details what was happening in the universe in the first few minutes after the Big Bang. So let's look at those information. Now there are three basic things that we need to pay attention. So when the universe expands, it gets cooled, right? Now in this first fraction of seconds, the universe was very hot, and we have actually have calculations that what has happened universe after 0.01 seconds after the Big Bang, right? And this tells us that the temperature has dropped to 100 billion Kelvin after 0.01 seconds after the Big Bang. And after a few 100,000 years, the temperature was further dropped up to around 3000 Kelvin, right? And universe is continued to cool since that time. You know that initially it was very hot, and once the things get expanded, they get cooled down, right? I mean, that's something that we know, right? So this diagram right here kind of give you an idea that how this temperature has dropped down, and here is where we are today from this yellow dot, and then this is the time where you have stars form. Very recently galaxies form before that, and then the atoms form after some time. Electrons and positrons are forming right here, and then the proton and antiprotons form around this region, and the radiation dominated in this region. Now this graph kind of tell you the whole story behind the Big Bang, right? Now this is the point right here where the Big Bang has started, and towards the right side it says the time elapsed since the Big Bang, the time it took for different things to happen after the Big Bang, and we are right here today, right? And you can see that earliest era just after the Big Bang, just after the Big Bang, it says earliest era rules unknown. The reason is actually at just after the Big Bang, the universe was so hot and so small that we cannot apply these gravitational theories that we know, and also we cannot apply these quantum theories, right? So you have to have something like something called quantum gravity, right? And these theories actually not yet fully developed that we can apply into this region, and this is why we talk what has happened after 0.01 second, because even before that it's hard to explain things like what has happened using the theories that we know up to now. And they were actually just after this particular, just after the Big Bang, all the forces are unified together, and we call this as grand unification theory. That is, there are basically four forces, right? Electromagnetic force, and we have weak force, gravitational force, and then there is a, what is the other force? I will show you all these forces. Basically there are four forces, uh, and all these forces are actually unified together just after the Big Bang, right? And then there are different times that they have separated and became the forces that we see right now, right? And so that's why it says forces unified. And initially you have a very hot universe. Because of that, the radiation you have a radiation dominated universe, and then after that you will have an era where you get protons and antiprotons form, and after that you get electrons and positrons stop forming, and then you have the atoms form, galaxies, stars, and it goes like that, right? This kind of explain the whole story about our universe, right? uh, the second thing is I told you that the universe was so hot. uh, at the same time universe get cooled down when it get expanded. And the second thing is uh, the universe was so hot that it uh, contained mostly radiation because of the higher temperature, right? uh, so what happened in this era was that the photons that filled in the universe could collide and produce material particles. So that is, under this condition, what happens is just after the Big Bang, energy can be turned into matter, and at the same time matter could turn into energy. You know this equation E equal mc square, right? So that's what happens there. And the next thing is, the hotter the universe was, the more energetic were the photons available to make matter and antimatter. Because of these photons are very hot, so they can create matter and antimatter particle. Now I have mentioned here an example, a temperature of 6 billion Kelvin. Two typical photons can create an electron and its antimatter counterpart. And at this particular I mean, and under this kind of temperature, what will happen is when you have two photons, they can create an electron and also its antimatter particle, which we called as the positron, right? Now, even if you go for temperatures, if it exceeds 10 to the power 14 Kelvin, then they can even actually produce protons and antiprotons, because these protons are much more massive particles, so they need higher temperatures to produce these. Right, so I'm not going to explain all these things that I have here. I just have a few more details mentioned here so that you can read through what has happened. So I have basically explained here when the universe was like around 0.01 second old. It has a soup of like matter and radiation both, and this matter included protons and neutrons, and then this each particle they collide rapidly with the other particles. So what will happen is uh, there are enough temperature to produce electrons and positrons at that time, right? And still like much too hot for protons and neutrons to combine at this particular point. And there was these neutrinos as well. You probably have heard these neutrinos. Neutrinos were actually some kind of particles that interacts very rarely with the ordinary matter, so that it's hard to detect those, right? And so that's what happens around like after 0.01 seconds. And then I have mentioned here what has happened around 1 second, and between 1 second and 30 minutes, these neutrinos will not interact with the matter, and they will travel freely throughout the space, right? But when the universe was about 3 minutes old, the temperature now slow down because it get cools down for up to 900 million Kelvin. And then there is a time that when cool down, there are different things happens at different temperatures, right? So when the temperature cools down, you can have protons and neutrons combined, which is the deuterium, right? You know about the deuterium, so you can make deuteriums, right? And also collisions also could convert some of them into helium atom as well, right? Now, if you take in essence, the entire universe was acting like a centers of stars, right? Fusing new elements from simpler components. That's what has happened in earlier universe, right? So what we have is we had some lithium at this particular point as well. So I'm not explaining like how they are formed and all these things due to the time limitation, but just get an idea how these things forms at the early universe. Now, after the formation of helium and some lithium, then temperature, now you have helium and lithium, and the temperature dropped little by little. And then there was a time that after you have lithium and helium, there were no elements beyond the lithium that could form in these first few minutes, right? And this was like we used to tell that end of the time when the entire universe was a fusion factory. So where you get all these particles combined and make lithium and then helium. Right. So let's, and this is kind of one picture that explains all these things. Initially, this basically explains everything that I have told up to now about this formation of different particles. Initially, you have photons uh, uh, combining together and make electrons and its antiparticles, and this happens to the reverse direction as well. Electrons and positrons combine and make photons, so it goes in both ways. And this is just after 10 to the power minus 2 seconds, right? And when the time passed and up to when it is like 3 minutes after the Big Bang, then you have the protons and neutrons combining to make the deuterium. Once you have the deuterium, it will combine with another proton to make helium, right? This is what has happened after that. But when the time has passed up to this 300,000 to 700,000 years, then there is an electron combined with the nucleus. so that you will have a complete atom, right? Make a neutral atom. And so this is what we have at the end, right? So I basically have explained here about that the fusion of helium and lithium was completed when the universe was about 4 minutes old, and it was still too hot for electrons to settle down and become associated with the nucleus. However, when it cools down more, the electrons and nuclei manage to combine to form a stable atom of hydrogen and helium. So now you have hydrogen. Now when this electron get combined to make the atom, then now you do not have any free electrons, right? So the advantage here is that once you do not have the free electron, the photons do not scatter, right? And we used to tell that at this particular point the universe became transparent, right? The idea is, if you need to see something, the light photons has to around, some kind of this electromagnetic photons needs to come to us. But until this time of the universe, all these light photons are scattered by these free electrons that you have. But when this temperature dropped down to this particular point, electrons get combined with the nuclei to make this hydrogen atoms. Now, when this thing happens, you don't have electrons, so that all these electromagnetic radiations or these photons uh, will go through the universe, right? And we used to tell that the universe became transparent at this particular point, which means if we have a powerful telescopes, we should be able to see everything up to this point, but not beyond that, right? Because all the light photons get scattered until this point. And we used to tell that at this point, the matter and radiation got decoupled from each other and evolved separately. And this is the point, the electromagnetic radiation could really travel, and it has been traveling throughout the universe ever since. Now, this is what we should be able to detect now, right? Because this is what is actually traveling. And now if we can detect this radiation that's coming on, we will have a very good evidence for the Big Bang theory, right? Now this is what explained here as the cosmic microwave background. As we look far outward in the universe, uh, far back in the time, the first afterglow of the hot early universe should still be detectable, right? So that's what I mean there. And actually, the astronomers and scientists tried to observe this afterglow, because if they can detect it, that could be a very strong evidence for Big Bang, right? Something they have predicted and they can observe it. So then you can kind of confirm that the Big Bang theory is correct. Actually, we have detected this radiation now uh, at this photon decoupling time, right? And that is the area that the universe became transparent. Remember, this is the time it became transparent, and electromagnetic radiation should have been traveling since that time, right? So we should be able to detect those. And the only thing is you have to be very careful here, because now the universe is expanding since that time. The radiation that when we observe it, they should be greatly redshifted, right? Because the universe is expanding, and astronomers have found that the amount of redshift, which means it should be peaked at around wavelength of 1 millimeter, and this is correspond to microwave region in the electromagnetic spectrum. Remember, initially it was not like that, but now it should have been it should be redshifted now, right? Because now we have spent like 13 some billion years now, so universe keep expanding. So these waves keep expanding because the universe the space stretch, the wavelengths also stretch down, so it should be shifted to larger wavelengths. And the prediction is we should be obtained, or we should be observe this in the range of microwaves. And also the characteristic temperature of this cosmic, we call this as cosmic microwave background because it's in the microwave region, and this should be around 3 Kelvin temperature. And also we assume that if it is there, that this should be seen in all directions in the sky. So this should be basically everywhere, right? And just to give you an idea, this is what I have kind of explained up to now. You have the Big Bang happened right here at time equals 0 and temperature equal infinity. And then you have something called inflation, which has just happened just after the Big Bang happened. And then you have this formation of deuterium and helium. And then this is the phase that you have this cosmic microwave background radiation or last scattering, right? Where you have this proton connected with an, so electron connected with the nucleus to form the atom. And this cosmic microwave background we should be able to detect it from here, right? The idea is, since the universe is expanding, this should be greatly redshifted and should be seen in microwave region. And if it is harder to understand, I have an analog picture here about the clouds that we have. And you can also, I may not have time to like explain all these things, just go and look at, in case if you can't understand, you should be able to easily figure out what is here, since I have an analog picture that when we see clouds in the Earth atmosphere, what happens. The idea is basically that, like, when once you have clouds, you cannot see beyond that, right? So the same thing happens here. So you cannot see beyond this particular surface where you have this last scattering surface. You cannot see anything beyond that. So everything that you will see will be up to this particular point, right? So this cosmic microwave background was actually detected by these two astronomers, Robert Wilson and Arno Penzias, in 1964 by using an antenna. And this is actually the diagram that shows you how these initial cosmic microwave background now we detect is redshifted from the beginning. Initially you have it in the range of gamma rays, and they are redshifted and came into optical range and infrared. Now it is in this radio wavelength region, right? So these are the two scientists, and this is the antenna that they have used to detect this cosmic microwave background. And by the way, this is something that has happened accidentally. They were not intended to actually observe this cosmic microwave background. Now we have separate devoted satellites. In fact, not one, there are few that observe this cosmic microwave background. And this particular, the line that you see here from the red line is the change with the frequency, the intensity radiation that should change with the frequency for a black body with a temperature of 2.73 Kelvin, right? You know these black bodies, right? I guess you probably have studied about the black body radiation. So the intensity that you basically see here, the curve, the red curve is the black body curve for a temperature of 2.73 Kelvin. And then from this cosmic microwave background, they measured at various frequencies, right, using this K.V.S satellite. And the data is perfectly matched with this curve. You can see that the small variations at different frequencies are nicely matched with the theoretical curve here. And here are different satellites that went out to observe these different, I would say, I mean, the same cosmic microwave background, but they have improved intense sensitivities, right? This Kobe is sent out around 1989 or something like that. And then after that, they have launched this WMAP satellite, which is launched around 2001 to look at the cosmic microwave background. And this Planck satellite was the most recent one in 2009. And they kind of show the same area that they have observed, but there are small variations are nicely detected from this later instrument because they have higher sensitivity, right? It's the same patch in the universe, by the way, just to compare what happens when you have higher sensitive equipment. And this map right here is the map of the cosmic microwave background, I guess taken from the Planck satellite. And these different colors basically represent different temperatures, right? So there are small variations in terms of the temperature. If you have sensitive instruments, you can measure that. Now, these colors, actually red color is, it represents more hot areas compared to the other colors where you have more cooler areas. So basically color is a representative of a temperature, and you can see that the temperature is not very uniform in everywhere. So there are small patches, you have high temperature and also for the low temperature. Now this is size of these hot and cold spots in this microwave background depends on the geometry of the universe, right? Hence its total density. Right now we are again going back to this geometry and the fate of the universe, right? And this from the general theory of relativity, Einstein showed that this curved space, the curvature depends on the amount of matter that is present, right? Therefore, this total amount of matter in the universe, including dark matter, and the equivalent matter contributed by the dark energy, determines the overall geometry of the space, right? Now, if the density of matter is higher than a critical density, then the universe will be eventually collapse. Now we are coming back to the same scenario that we discussed before, based on the results that we have from these variations of the cosmic microwave background, right? Now, if the density of the matter is higher, because how, just get the connection here, the sizes of the hot and cold spots in the cosmic microwave background depends on the geometry, and this is then connected to this density, and there are three geometries that we can call about the density based on the density of the matter that is higher than the critical density. The universe will collapse, as we told previously. And what will happen is, this is universe is collapse means it should be a closed universe. If it is a closed universe, parallel rays of light will eventually meet one day, right? Because this geometry, right? And this geometry is called as spherical geometry. And there are two other geometries. If the density of matter is less than the critical density, then the universe will expand forever. Once again, the same thing that we have explained. And in terms of the geometry, what will happen is, if you have initially parallel rays of light, they will diverge. And previous case, you have two parallel rays that will converge. And here, if we have two parallel rays, they will diverge. And this is referred to as the hyperbolic geometry. And if you have a critical density uh, equal to the current density of the universe, then these parallel light rays never meet, right? And the expansion comes to a halt only at some time infinitely far in the future. That is the third possibility, which refers to as a flat universe, right? And this is where the Euclidean geometry is valid, the geometry that we are using. And in terms of diagram, this is what could happen. And remember, this is the critical density that we talked before, and that is kind of related to the geometry of the universe based on this critical density, right? Now, if you have a spherical, if you have a critical density greater than the critical density, then you have spherical space where you see in the left hand side, and in the right hand side is where you have the hyperbolic space depending on the critical density that you have, and then you have the flat space if you have exactly the critical density in the universe, right? And these are the current measurements actually for the omega parameter, which is the cosmological density parameter, right? We talked
This is also the ratio between the density and the critical density. And there are different quantities contribute from different types of uh, matter and energy. What we know is we have matter, dark matter, and the energy in the universe. And the contribution from the matter will be 0.05, and the dark matter 0.25, and dark energy is 0.70. Now, what this tells is surprisingly that the current universe has a density, cosmological density parameter that is very close to 1, right? If you add these three, 7, 2, 5, and 0.5, that is, I mean, very close to 1, right? Now, that means what? If this density parameter is equal to 1, what that means is our density of the universe is very close, so approximately equal to the critical density value. So when that happens, you can see the condition here. When in the critical density universe, when the universe density is equal to critical density, two parallel light rays never meet, and the expansion comes to halt only at some time infinitely far in future. And this particular universe is what we called as the flat universe, right? And remember earlier also we talked about this. If I go back right here, remember that we talked about this density parameter, that is the observed density divided by the critical density. When this is equal to 1, what that means is the observed density of the universe is exactly equal to the critical density, right? Then I have told that the universe is especially flat at this condition, at this particular point, and it is infinite. And this is what we have obtained right now. According to the data that we have, the universe is actually has this omega parameter equal to 1, which means the universe is especially flat. And yes, so this is actually what we know up to now. However, I mean, this may change in the future with the new results, right? So we cannot rule out any of the other geometries, but what we think now is we are living in a flat universe. That is the idea, right? Now here are some data actually came from this latest Planck satellite. That is this satellite right here, this one right here, that gave you about these small deviations in the temperature of the small deviations in the cosmic microwave background, which tells us the size, these hot and cold spots depends on tells us the geometry of the universe, right? So that's how you have all these data and details. And what it tells us is age of the universe is approximately now 13.799 billion years. That means we know the age of the universe to within 38 million years. Uh, I mean, accuracy, right? And the Hubble constant from the latest result is the value is 67.31. We normally use this as 70 in nowadays, and the unit is kilometers per second per million parsecs. And the fraction of universe that content which is that is dark energy is around 68.5, and then the fraction of the universe content matter will be around 31.5. Now this is kind of the latest results that we have from this Planck satellite. And this is again previous details again compared with the observations that we have for the cosmic microwave background with the possible models of the universe, right? Now then, I guess we are kind of, what is the time now? We may be just running out of time now. And some of the extra things that you can look in here, and here is kind of a representation of what we know up to now. In terms of, in 1970s, we thought that the visible matter is around this, the portion is from this yellow color, and then the ordinary matter is what you see from this blue color. And then it actually changed in 1980s. We thought that we have dark matter amount by this amount, and ordinary dark matter is what you have from this blue color, and the amount that you know is ordinary visible matter is very small. But now it has changed in 1990s. Now you have the dark energy in the most of the part, and then dark matter, and then exotic dark matter, that is what they call, and then you have the ordinary dark matter, and then the small portion of visible matter, that is what we know. And what you can think about from this idea is that we actually don't know much about the universe now, right? So there are a lot of things that still needs to be explored. Right now, the dark matter is 27% composition of the universe. Right now, the dark energy is around 68%, and ordinary matter is only 5%, right? This is what we know, right? Ordinary matter is hydrogen, helium, stars, and other stuff, right? So this is the amount that we know about the universe. That's what I can tell at the end, right? So it is a very small portion that we know about the universe. Everything else right here is open for research now, right? So we don't know much about this area, and this is why people started building larger and larger telescopes now, right? Look at this, more and more into the space, right? Now this is a nice image actually that summarize everything that we have talked up to now. And just look at where you have the Big Bang right here with small quantum fluctuations, and you have this huge inflation, and we did not talk about that much. And then you have this after around 375,000 years, you have this afterglow light. This is where you should have detect this microwave, cosmic microwave background, and after that atoms and these things form, hydrogen atom formed, and then you have first stars after 400 million years. And with the time goes on, you have development of galaxies and planets. And this is probably, I guess, one of you have asked about this, the very first generation of stars one day, right? I mean, they are kind of in this region. And by the way, if I can't remember, I mean, they still have the same constitution. Like when you have a hydrogen is what they have as the first stars, but they are the first generation stars. Maybe not have much metals there. And then you have this dark energy accelerated expansion right now. So that's why this curve is kind of directed towards the upward direction, right? And I have a small model here for the to show you the inflationary area of the universe. It is this part right here, where you have a huge expansion of the size within a very short period of time, right? So that inflation is needed to actually explain some of the stuff uh, that we have, which we did not have time to talk. And and I would like to explain this last slide as the final point. This is actually is what has happened in initial time, and this is time after the Big Bang. You can see that after 10 to the power minus 43 second, all these forces are unified together at the beginning. That is the nuclear force, strong nuclear force, weak nuclear force, electromagnetic force, and the gravity. All these things are unified right here. But after some time, they started to break down into these different forces. The gravity goes away, went away first, and then all these three were unified for some time, and then the strong nuclear force is kind of decoupled, and then you have electromagnetic and weak nuclear forces together sometime, and at the end you have electromagnetic force separated with the weak nuclear force, right? This is a different story, and this is in fact called as the grand unification theory, if you don't know about it, right? So maybe I have not mentioned here, right? So that kind of end up your lectures. uh, right here, actually what I wanted to explain is, it is true that some of these very final slides you may not have gotten the complete idea, but that's okay, because some of them are actually some extra details for those who need to read through. but you need to get the basic idea, right, about the Big Bang, like things that has happened. So everything in the slides, I kind of expect that you will know about these things. And at the same time, um, this complete new set of slides is made using this book that I ask you to refer in this OpenStax website. And if you go and read this chapter 29, all these details are there, right? So if something is not clear, please go and read that chapter. It has lots of details, right? If I'm going to put all these things here, then I won't be able to finish, right? And you can see that even this one I cannot finish, I mean, all the things. So make sure that you go and look at it, and but just get the basic idea as students who have done astronomy course. Right, so that will be end of that section. And I mean, the reason that I stop right here, I would like to get probably 10 or 15 minutes to talk just some extra things with you, not about the syllabus or things that we talked here.